Hello everyone, my name is Daniel McCrum. I'm from the School of Civil Engineering in University College Dublin, and I'm presenting the work we've done on cold form steel moment resisting frames, mostly about testing today. Um, this work has been in collaboration with partners in University of West Scotland, Trinity College Dublin and the University of Auckland, so that's Andy, James and Brian. And funding, this project was funded by the Institute of Civil Engineers, and materials provided both by Stedman's and Capital Steel Building. So what I'm going to talk about today is what we were really investigating was the difference between these true fit and oversized bolt holes. So true fit connections, what we were really looking into was, so if you have self-tapping screws, which are limited to 10 millimeters approximately in diameter, what if you could create a similar kind of performance using larger bolt holes with perfect fit almost around the bolt hole, so the bolt size is the same as the bolt hole dimension, and see this, how does the performance vary compared to oversized connections, the standard oversized connections where you have 2 millimeters holes. We did this using monotonic testing, cyclic testing, and we did seismic testing as well. Okay, so we checked it under all of these conditions. So when we were looking at true fit versus oversize, if on the left-hand side, if you look at these normal tolerance bolt holes, you have, this is just two plates and you're pulling them apart, and you have a bolt in there. You get that slip phase and then the bearing phase, okay? And on the right-hand side, these true fit, there's almost no slip, okay? Because the bolts are M18s and the bolt holes are 18 millimeter diameters as well. So you can see you have no slip phase. So we wanted to understand how the performance would vary, okay, for these two types of connections in moment resisting frames. So this is one of the test frames. We had 3 test sizes. We categorized them as, these are back-to-back channel sections with haunched connections, and hopefully you can see the bolt groups as well. We had strain gauge locations recording the strain in the columns. We had the actuator pushing the test strain backwards and forwards. So this is the lateral resistance or lateral capacity that we're interested in. We had outer plane restraints as well to hold the frame in position. There were 3 different test frames that the dimensions approximately were, I think 3.2 meters wide and 2.2 meters high, something like that. And we had 3 different back-to-back channel sections that we investigated. Approximately 200, so these are C218, so they're 200 millimeter deep sections. C250 20, so approximately 250 millimeter deep sections, and then C325, so approximately 300 millimeters deep. And that's what I think you can see here. So on the monotonic test, obviously we just push over until we reach the test ends, essentially, and we get past the peak. On the left-hand side, you'll see the normal tolerance bolt holes, and on the right-hand side, you'll see the true fit, is what we're calling them, or the perfect fit bolt holes. The performance was pretty similar for both of these. So we didn't see a huge variation in terms of ultimate loads or peak loads. There was some variation in peak loads, but we didn't see a huge variation in terms of performance, okay? When in the monotonic testing, though, what we were kind of interested in was understanding the behavior, okay, the mechanisms through which these frames, how they performed, how did they transmit the load from the actuator and down into the supports. So we did a framed analysis, a very simplistic framed analysis using robot software, and from this we were able to derive the stresses in the members. So the rotational stiffness of the 2 moment resisting joints in the top left and right of this image here, we got these from the experiments that we did. So the monotonic test, we were able to work out the rotational stiffness of the joints. So that allowed us then to derive the stresses in the columns, for example, and then we use CUFSM software to utilize the internal forces from the framed analysis to help us get the stresses in the channel sections. And then we compared this to the test data. So in the figure on the right here, we can see we have a channel section and with the strain gauge location. So this was just below the haunch, really, on the left-hand side column, so to speak, as you were looking at the test frame. And we got very good agreement between the analytical stresses and the measured stresses. And this is we did it at 30% of the peak force, so kind of in the elastic sort of region, 70% of the peak force, which is much closer to design. And we also did it at the ultimate or the peak force as well that we observed in the test. So very accurate for 30%, 70%, and less accurate as you would expect at peak. Okay, so this enabled us to then understand what all the different stresses were in the column sections. So what we have here is a table again. This is of the C250-20, and this is at 30% of the peak load. So we compared the strain gauge results to the CU-FSM results, and we got very good agreement. There was a 9% difference here for the C250-20, but in the C218 it was only 5%, and in the C320 it was closer to 20%. But what we noticed here is when we broke down the stress, the summation of all the stresses using the analytical method, we found that major axis bending obviously was the majority of the stress component, but after that it was the bi-moment was the next largest, and it counted for around here in this example about 22-23%, and that was typical for the other specimens as well. So that was really important finding that the bi-moment is really important component of the overall stress within these stress distribution within these specimens. We then moved on to cyclic loading. When we're doing load cycles here, you can see in the bottom left figure, you need the first yield point to give you all of these cycles, okay? So you do delta y over 4, delta y over 2, you do certain cycles, etc. And this is a European standard. The question, so in hot rolled steel, it's very easy to pick the yield displacement, okay? You know when that first yield occurs, it's very easy to pick. However, in cold form steel structures, that's not so easy to do. So there's a European standard as well, that the references at the end, where this is one of the monotonic pushover. I think this is for the C250-20, or it might be C300 actually. No, it's C250-20 because it's 60 kilonewtons, yeah. And what we see here is that you get the initial stiffness, okay, and then you have the peak force, okay, the ultimate force. So you come up the initial stiffness, you draw a line, and then at peak force, you do the initial stiffness divided by 10, and you bring that line down. And where those 2 points meet at point A, this then gives you your delta y, okay, your first yield. So it gives you yield force and your yield displacement. And you can then use that to create your load cycles. So that's how we do it. Here are, okay, the acronyms here are PTVH, which is perfect tolerance. So that really should be true fit ones, okay? So PTVH are the true fit bolted connections, okay? And NTVH are the normal tolerance, okay? So the standard 2 millimeter tolerance. So what we saw is there's very stable hysteresis plots, okay, for all three specimens, okay? The C300 was quite stiff, so we didn't really get that far past post-peak, okay? But you can see the stiffness degradation is quite smooth, and the hysteresis loops are quite consistent, you know, they don't degrade too suddenly. This is what we saw at the end of, this is the C250-20 experiment, and these are some photographs at the end. So you can clearly see we had local buckling in the web, we had buckling in the flanges, we observed tearing in the web flange connections as well, okay, towards the end, okay. So I'll come on to what we made of this later on at the seismic one, actually, I'll come on to that later. So then when we looked at the cyclic performance, what were we interested in? We were interested in the ductility, energy dissipation, okay. So we looked at each of the different test frames, what the ductility was, and what this is the yield ductility. So we're using that delta Y value. So what was the difference in ductility? So between the frames, it was about 5.5% on average, okay? But actually we found that dissipation, so the total energy dissipation actually was considerably bigger, okay? In and around 20%, 22% I think here on average for the 3 specimens, okay? So a real improvement in the normal tolerance bolt holes, which makes sense, okay, compared to the perfect fit, because you have that sliding every time in each test phase, okay? You have that sliding backwards and forwards, so that's helping to dissipate energy. Finally, we did some hybrid seismic testing, so we did real-time testing. This was for a Taiwan earthquake in 1986. And here we have, you know, the numerical part of the structure and the physical part of the structure. So we tested the physical part and the results feed into the numerical, but really it was the true testing of the frame at real seismic loading that we were just interested in see what happened, okay? So what we noticed here, if you look at the test results for this, is that we were just interested to compare them, the test frames, you know, what were the peak loads, etc. So the peak ground accelerations we used for the Taiwan, so we scaled them ×1, and that's 1.53 G, okay? And then we scaled them as best we could after that. And these are subsequent tests after. So test 1, test 2 follows test 1, and test 3 follows test 2. So considerable amount of damage, okay? So when we scaled it ×1, you can see here we didn't have a huge amount of nonlinearity, okay? And not unsurprising because the loading is so light in these structures, you know. And again, when we had the maximum scaling tests, again, not a huge amount of nonlinearity, okay? And again, the reason for this is really because the masses are so light. So finally, just looking at the performance, so how do we sum up the performance? Based on our results from the cyclic and from this as well, this photograph is the first buckling point in the test in the C325, you know, that initial buckling of the web, that's what happened first, and that's what we observed, okay? But the frames in general performs very well under extreme loading, okay? They fail through local buckling, okay, in the column to haunch connection, and the failure mechanisms don't align with the strong column, weak beam. So we get failure in the column, not failure in the beam. So that was something that would have to be addressed. And finally, just to summarize, so the performance was quite similar between the normal tolerance and the true fit tolerance connections for the monotonic response, okay? It wasn't too dissimilar, okay? But what we did notice is that the bi-moment component is, for both actually, the normal and the true fit is quite high, okay? It's 20%, it needs to be taken into consideration, okay? They perform well under seismic loading, however, the failure mechanism does need to be addressed in terms of strong column, weak beam, okay? Thank you very much.